Let's do a few examples of natural deduction proofs for predicate logic. In fact, we'll do a couple of examples of proofs that do work, and then at least one example in the middle of a proof that actually isn't possible to see how some of the restrictions on the rules block us in that case. So here's an example. We have for all x, Rxa implies Rxx. We have for all x, Rxb. We have b equals a. Those are our three given formulas, and we need to prove for all x, Rxx. This is relatively straightforward, but let's go through the steps and see how this works. So often what we'll do for a proof like this is to write down the given statements at the outset. So I'll just write these. Nothing really happening here, but just writing down the given steps. Okay, so now what I'd like to do is prove for all x Rxx. So that's going to involve the introduction rule for the universal quantifier. If you think about how that works, remember we'll need to introduce a new constant symbol. In this case, c will work. Actually, let me put it over here to the right as we did when we wrote down the rule in the first place. C is a new constant symbol which doesn't appear in the original language of the formulas we have in the problem, and it doesn't appear and will not appear anywhere outside of this subproof that I'm starting to construct. In other words, we're saying let C be an arbitrary member of the domain that we're working with here. And let's see what we can do. Okay, well, what do we have here? We know that for all x, Rxa implies Rxx. So if I apply the elimination rule for the universal quantifier, then I can deduce for all x, or sorry, not for all x, that would go away, but plugging in c for x gives me Rca implies Rcc. So that's by the elimination rule for the universal quantifier. Now notice RCC is actually what I'd like to prove within this subproof, because I'd like to then more or less generalize to give myself for all x Rxx at the end. So if I can show RCA, then I should be in good shape here. Okay, what can we do next? Well, I do know for all x Rxb. So applying that would give me RCB in the same way. That's the sorry, I'm using two quantifiers there. The elimination rule, that's an ordinary E, for the universal quantifier. There we go. So I have RCB and I have RCA implies RCC. Of course, the missing link here is B equals A. So I need to do that substitution. Here's an example showing you how the rules for identity work. I have RCB, but I also have B equals A. So remember, as long as we're substituting into terms that don't contain any bound variables, here we don't have any variables at all, we only have constants, and as long as any variables being substituted don't become bound, again, not a problem here, then we can substitute. So I can replace B with A to give myself RCA. So that's by the elimination rule for equality, using the given equation B equals A. Okay, well now that I have RCA, I can prove RCC. That's my modus ponens, or the elimination rule for implies. So notice what I've done here is to say, starting with an arbitrary element C of the domain, I can prove RCC. Well, now I'm ready to use the introduction rule for the universal quantifier and say for all x, Rxx. That's the introduction rule for the universal quantifier. That makes sense because, again, this new constant that I introduced, c, doesn't appear anywhere outside of this subproof. So that's a legitimate use of that rule. Here's another example, and I have some question marks over here because this actually isn't going to be possible. I'm going to try to prove for all x exists y Rxy implies exists y for all x Rxy. If you think about it, this is the situation where we've discussed this possible logical implication doesn't actually work. The left-hand side does not logically imply the right-hand side. So we shouldn't be able to prove this, but let's see if we can figure out what goes wrong here. If I start trying to prove this, well, let's see. First, I would actually need to show the existence of y. So maybe the best way to get started here is to use what I have in the given statement. In other words, maybe I can actually just replace x with itself and prove exists y rxy. So that would just be from the elimination rule for the universal quantifier. Now, if I'm going to work from exists y rxy, here's where I would probably need, or I would naturally want to introduce a new constant. I'll call it c. And the new assumption that I would want to work with would be rxc. In other words, I'm saying, well, I know there is a y that makes something true, so let's use c as the representative or the name for that object. Okay, well now let's look over here at the right-hand side. I'd like to show that for all x, or I'd like to show that there is a y. There is a y such that for all x, rx, y, and I have c, which actually seems like it might kind of give me what I want. But notice I'd like to generalize based on x at this point. So, what do I need to do to try to make this work? Of course, it isn't going to work ultimately, but what makes sense in this case? Maybe I need a new constant d. Let's introduce a new constant d. I'm going to attempt to prove the universal statement for all x rxc. Now, if I do that, I need some way to basically substitute d for x. I mean, that's what I'd like to do. But notice I don't actually have a universal quantifier applied to x here. So I'm kind of stuck. I guess you could say, well, maybe I should go back to the original statement and use that universal quantifier again. I would then get exists y r dy. That's again from the elimination rule for the universal quantifier. But notice now I'm in trouble. This is probably where maybe I should stop this proof, which isn't ultimately going to work anyway. If I try to work from this existential quantifier using the elimination rule for that quantifier, I would have to introduce a new letter for y. In other words, there's no way to get back to c and somehow connect it with this d. So the rules really do lead to trouble here, which makes sense because in fact the left-hand side here is not something that we're going to be able to use to prove the right-hand side, because the left-hand side does not logically imply the right-hand side. But this is the kind of situation that we can get in. The rules are set up so that they prevent us from proving things that are not valid. Okay, let's try another example where we will be able to complete the proof. Very similar statement. Here we're going to show that exists y for all x rxy can prove for all x exists y rxy. What we're going to find here is that the sequence of quantifiers works perfectly to make this possible. So let's do it. We'll start with exists y for all x rxy. That's our given statement, so I'm writing that down to begin with. Now I'd like to show this universal statement on the right-hand side. So remember, how do we do that? Well, we're going to need to use the introduction rule for the universal quantifier. So let me set up a subproof. I'll make it nice and big here. And I'm going to say I'm going to introduce the new constant, or the new parameter c. That's my arbitrary object, which I'm hoping to eventually replace with for all x here. So what do I need to show? I'd like to show there exists y rcy. Well, I think at this point I can now use the existential quantifier on the left-hand side. In other words, I can use this given statement. Now there is going to be some nesting of subproofs here, so let's be cautious. We'll have to see exactly how this works out. But what I'm claiming here is that now I can introduce a new constant, let's say d, in a subproof. And here my assumption is going to be for all x rxd. Right, I'm saying, well, I know there exists a y that makes this true, so let's call that by the name d. There's my assumption. I'm setting myself up for the elimination rule for the existential quantifier. Okay, well, notice now I have for all x rxd, and I'd like to prove that in fact c falls into this role played by x. That's no problem because I can just deduce RCD from the elimination rule for the universal quantifier. That's no problem, actually. That's just fine. Now, what can I do from here? Let's be careful and see what we're trying to prove here. We're trying to prove for all x exists y, Rxy. So what I'd like to do now is to basically get rid of d, or replace d with the existential quantifier. This is the introduction rule for the existential quantifier, and this is perfectly fine. I can say exists x r, sorry, let's get the variables right. Exists y, there we go, r c y. Using x would be okay there too, but then I wouldn't get the correct usage of variables that I want in my final goal here. So that's by the introduction rule for the existential quantifier. And remember, there aren't too many rules there, or the only rule is we wouldn't want to, if we think of going the other direction, substitute something for y that becomes bound, or that contains variables that become bound. But here we're only dealing with a constant, so that's fine. Okay, well, what I'd like to claim here is that in fact now I have a conclusion in this innermost subproof, which notice doesn't depend on d at all. So I can close this off and I can say, well, now I can claim that I have exists y RCy. That's by the elimination rule for the existential quantifier. In other words, I'm saying that follows from this given statement here, or given formula here. I don't need d to make this work. But notice, what do I have now? In fact, I think I'm almost done, because I've shown for any arbitrary element c of the domain, I have the formula exists y RCy. Well, that means that that should be true for any object c, or for any object x, if we want to phrase it that way. So now I can deduce for all x, there exists y Rxy. So that's from the introduction rule for the universal quantifier. Remember, that's the more complicated one. That's why we introduced c here at the very beginning of the proof. We showed that, in fact, the desired conclusion that we wanted does follow for an arbitrary object c. So it might be useful, if you want to take some time, even think about it on your own, see if you can convince yourself that there is an important difference between the previous example, that we didn't get to work from model theoretic considerations shouldn't really work, but you might try some other approaches and see if you get stumped or get blocked in a similar way, versus this example, which looks very similar, but of course we are proving something that we know, or I think have at least argued, is a logically valid implication. And in this case, the rules work very nicely to give us what we want. So there are some examples of the natural deduction system for predicate logic which you can refer to as you're doing some of your own proofs.